So we got Quiz Wednesday, all right, Calculus Carols Thursday. If anybody would like to do that, I hope some of you do. So today we're going to finish up some discussion on limits. We're going to add another thing that you heard. I don't remember if it was one of the Calc Carols I played here, the other class. I thought we did this on Friday. And one of the things they talked about in there was L'Hopital's rule. Somebody in their lyrics had L'Hopital's rule. We're going to talk about that today for limits. Okay. And then, of course, before that, we had the particle motion stuff, which isn't really a section in the book, but it's just a big idea, the type of problem that's on the AP test all the time. And so just a good kinds of problems to do. So those two packets that we had, and then we'll finish up that packet tomorrow, this one. And then, again, go back and review this one, especially like the graphs and the tables, because I might put some of that on there too, where you're given a certain graph, a velocity graph or position graph or a table of values. And so just so you can do kind of a problem with all those kind of things. And so review that and see if you got questions to bring up tomorrow about that. So I just thrown a couple things up here that I think are important. Of course, the chart, position, velocity, acceleration, F prime, F double prime, that's all, so if I ask a question, about when is the particle moving to the right, that's kind of like when its position is increasing, that's when its velocity is negative, or positive, to the right. So it's, a lot of the stuff in the chart is important to know. If you ask a question about the velocity, when's the velocity increasing or something, we'll think of the chart. This row, this is increasing when this is positive. So when acceleration is positive is when velocity would be increasing, right? Which is actually when the position function is concave up, right? Velocity is increasing when this is concave up. So, just if you know the chart and position, velocity, acceleration have that relationship, that can help you in a lot of questions. And we added some other things too. Displacement is just the distance between the starting point and the end point, right? Even though it moved around, like if I drive from here to Lincoln and back to Gibbon, and that's my ending, my displacement would be just the distance from here to Gibbon, right? That's the difference between the beginning and the end, the net distance traveled. Total distance traveled, I'd have to add up the distance between my stationary points, or resting points we call them, right? So we need to know when we stop. So if I go to Lincoln and I stop, I turn around, come back to Gibbon, my total distance traveled is from here to Lincoln, and then add on Lincoln to Gibbon, right? So we got to find those different spots. It was almost like a list of candidates. We had to find where we were when we started, where we were when we ended, and where we stopped, where we were when we stopped. We have to find all those places, and then we add up the distance between them. So we'll go back and practice that some more in class. I think you'll have some work time tomorrow to do that. And then, when is your speed increasing, decreasing? Remember, that's different than velocity. Speed is the absolute value. I probably should put that up there too. Speed is the absolute value of velocity. Okay, and I think we've talked about that, but it probably maybe not even in those terms. We've talked about how speed's always positive. Speed is the absolute value of velocity. So we can't put speed in the chart, right? It's position, velocity, acceleration, F prime, F double prime, but speed is different. Speed has to take into account both acceleration and velocity. Okay, so acceleration and velocity, if they have the same sign, then the speed is increasing. So these two columns both have to be positive, right? For the speed to be increasing. And if the speed is decreasing, if it's slowing down, that's sometimes how it asks the question, is it speeding up, is it slowing down? If the speed is decreasing, then acceleration and velocity have opposites. Okay? So those are some things we kind of added into the mix that are, beside the chart when it comes to these particle motion problems. Okay? All right, so there'll be a number of questions about that on the quiz. And then, of course, what we've been working on here now with limits. All right. So, questions on the homework? Oh, I should teach Hamilton around. We have the homework done? Lazy. After Christmas. New Year's resolution. All right, let's assume everybody's got it. Couple things I'm going to talk about before, but give me some numbers here you want to look at. I'm thinking especially on 9 through 21 there. Probably could go through all the answers real quick. 19. Yeah, 19's a good one for sure. You know what? We can run through the answers to that real quick. We can run through that'd be good. That'd be good for us anyway. All right. So let's before we do that though, let's just talk about a couple of things here just to recap from last week. So the black was the old stuff, the stuff we've done with limits before. That's still going to be on the test. The quiz, what we've added to it is if it does not exist, we have to go farther. Typically does not exist is going to involve infinity, quite honestly, because if you think about it, about the only way, well, I mean, here, let me go to the next slide. Basically, if a limit does not exist, a couple of things, first of all, cars don't meet. That's probably one of them, okay? Well, if the cars don't meet on one like this, what's the equation of this going to look like? Piecewise. It's got to be a piecewise function, right? It's pretty much got to be a piecewise function, and so that's going to be pretty obvious. And I might give you one of those, right? I might give you some of those. I might give you some equations that are piecewise functions. So you're going to check, okay, right here at 2, this is braking, and so on the left it's 4, on the right it's 6, and so the cars don't meet, and so you could do that graph, plug in a 2 into one equation, see what you get, plug a 2 into the other, see what you get, right? So, but that's going to be pretty obvious. That's going to be pretty obvious. You see a piecewise function, you're thinking, okay, might have something like this. What's not going to be as obvious is when you get an equation with a vertical asymptote, right? So that's kind of the new thing we've added. So before, if you plugged in and you got 6 over 0, you just said does not exist. It's undefined, so it does not exist. But now we understand, hopefully we're understanding, we get 6 over 0, that's a vertical asymptote. Okay, and so what we probably have is something like that, which the cars clearly don't meet. So on this one, if this was a 2 right here, we'd say x approaches 2 from the left is going to infinity, and x approaches 2 from the right is going to negative infinity. That's what we would say for that one. Okay, now you also might get a vertical asymptote, though, that does this. Okay, now on this one, you could say x approaches 2 from the left is infinity, and you could say x approaches 2 from the right is also infinity, but I would probably accept on this one if you just said infinity, right? Does not exist, infinity. You check both, they're both going to infinity, we just say infinity. Again, the cars still don't meet, so it's still a does not exist. Okay, now the other example of a does not exist would be as x approaches infinity, and the graph's just going off like that, right? I mean, now, so anytime we're doing, these are all as x approaches 2, right? So as x approaches 2, you got the cars from both sides, right? But if x approaches infinity, we don't have the other side of infinity. So x approaches infinity, we just got one car. And it's not heading towards a number, it's just heading out here into space. Going to infinity, going to negative infinity, right? Instead of a horizontal asymptote. So if it's coming down here and it's coming down towards 7, right? Then we got a horizontal. So then the limit is 7, okay? So those would basically be your examples of what's happening with the does not exist. The cars don't meet, or the graph's just going off into space, okay? Either up or down. All right. So most of the time it involves infinity, right? Most of the time does not exist involves infinity, except maybe in a piecewise kind of function like this. All right. All right. So talk about this a little bit. This was up on the screen right at the end on Friday, and then I decided not to talk about it because we had enough going on and so forth. So this is going to kind of lead in, and this may help on our 9 through 21, which was okay that we hadn't talked about it, but so you still could think your way through it, but now maybe we can clarify a little bit if there's still a little bit of uncertainty with this. So infinity is kind of strange. Matter of fact, if you would open your books, to page 223. 223, please. There's a good little table down there at the bottom. So again, infinity is not a number. Infinity is not a number. Okay? We kind of treat it like a number at times, but we got to understand it is not a number. So when we say 1 over infinity equals 0, they say that's usually okay, but what we really mean to say is as x approaches infinity, 1 over x is approaching 0. So they say, why not say so? But a lot of times I will do that. When I see 1 over infinity, I will think to myself, or 7 over infinity, or even 1,000,000 over infinity, right, is still 0. 1,000,000 over infinity, what that means is you got 1,000,000, which stays 1,000,000, divided by something getting bigger and bigger and bigger and bigger and bigger. So that fraction is getting smaller and smaller and smaller and smaller. Okay, as the bottom gets bigger and bigger and bigger. So it doesn't matter what constant you have up here, if the bottom is going towards infinity, this is going to be 0. So a lot of times we just think of that. Now, along those same lines, when I see 1 over 0, or any number over 0, any constant over 0, I typically call that infinity. Now, again, that's technically not a true statement with an equal sign, because infinity is not a number, so it can't be equal. But that's kind of what they're saying. And I think they say that in the middle there, the fourth one down, it says 1 over 0 equals infinity. Now it says wrong. Division by 0 is not defined. Worse, 1 over x approaches infinity as x equals 0 from the right, but it's negative infinity from the left. So it's really not, I just like to think of it, I guess maybe I should write it this way. So what I would like to think of is some constant over something getting big is going to get what? Small. Now, when we say big and small in here, we're basically big means infinity, small means 0. Okay? And if we have something divided by something really small, what are we going to get? Something really big. Okay? So again, that's kind of what we're saying. So whenever, for most of the time when we think about it, we can kind of think this, right? Of course, that's why you can't divide by 0, right? The reason you can't divide by 0 is you're dividing by the smallest number. If you could divide by the smallest number, you'd have to get what for your answer? The biggest number. There is no biggest number, right? That's why we can't divide by the smallest number, because we can't. The answer would have to be the biggest number, and there isn't such a thing. Okay. All right. So. And then 3 times infinity. It says, okay, as mathematical shorthand, 3 times infinity equals infinity. Basically what it means, if the quantity increases without bound, then so does 3 times that quantity. So 3 times infinity equals infinity, yeah. I mean, but again, as we're going to see in a minute, there's different sizes of infinity. All right? So those are things that are okay to kind of talk about. Again, infinity plus infinity is infinity, kind of the same thing. Infinity minus infinity is 0. That is totally wrong. We're going to look, I guess we're not in our examples here. But again, because of different sizes of infinity. All right? And we're going to see that one of your problems today, it had 2 to the x on top. It had x squared on the bottom. Remember that? 2 to the x on top, x squared on the bottom. Both of those are getting big. But 2 to the x is way, way bigger. Right? So if you took, I don't know if we run into this problem. Okay? If you took that right there and let x get really, really big, those are both getting really, really big. The one on the left is getting way bigger. Okay? Matter of fact, 2 to the 100 compared to 100 squared, not even close. 100 squared has 4 zeros. 2 to the 100. You see what I mean? So it doesn't take very long to put a number into here to make this so much bigger than this that this basically becomes insignificant, like Warren Buffett. You got this minus an insignificant amount. So there, infinity minus infinity would be what? In that case, as x gets really big, what's that going to be? Infinity. Does not exist. Infinity. That's one, because this is so big minus a little amount, it's just getting bigger and bigger and bigger. It's going to infinity. So infinity minus infinity there would be infinity. Now what if I flip those around? Negative infinity. Not zero though. No, that's we got to think, right? Because we're not dividing, so it's not getting smaller. But what you'd have is zero. If you flip these around, you'd have zero minus infinity, right? Basically, you'd have something insignificant minus infinity. It'd be negative infinity. It'd be going to negative infinity. So again, infinity minus infinity would not be zero. Okay? Infinity divided by infinity is 1. No. Okay? And that's what we're going to see if we divide these two. Okay? Which we're going to see on those problems here in a minute. And then the last one, 0 times infinity. I kind of mentioned this, I think, on Friday. When we say 0 times infinity, what would mean is something getting small times something getting big. Now, when you multiply by something big, it wants to make the product bigger. But when you multiply by something small, like 0.1, 0.01, 0.01, when you multiply by something small, it wants to make the product smaller. Well, these two are fighting against each other. What's going to happen? Well, let's look at 3 examples. Each one of these down here is 0 times infinity, if you think about it. Would you agree with that? As x gets really big, this is getting really small, towards 0. And this is getting really big. This is getting really small. This is getting really big. This is getting really small. This is getting really big. So we have a 0 times infinity situation. Okay? Now, what's 1 over x times x? 1. So as x gets really big, doesn't matter. This will be a billion divided by a billion. A trillion divided by a trillion. It'll be 1. So there, 0 times infinity is 1. Okay? What's 1 over x squared times x? 1 over x. So as x gets really big, what's this go to? 0. The 0 wins. The 0 wins. Why? This is squared. So this is getting small faster than this is getting big. Remember when I said that the other day? The 0's winning. The 0's getting small, or this thing is getting towards 0 faster than this thing's getting big. So the 0 wins. And so the answer is 0. Okay, and then the reverse is true here. Right? What's 1 over x times x squared? X. So as x gets really big, what's this do? Getting really big. Right? The big one wins. Infinity wins on this one. This is getting small, but this is getting big faster. And so it's going towards infinity. So 0 times infinity could be a number. If I'd have made this 3 over x, then the answer would have been 3. Right? Or 7 over x, the answer would have been 7. I could have made it come out anything I want. So 0 times infinity could be a number. 0 times infinity could be 0. 0 times infinity could be infinity. All right? So again, that's called indeterminate. We're going to get into that here in a little bit. Okay. So I think I maybe just have them all written down here. So let's go. We can just quickly go through this. So what do you have for 9? 0. 3 over a really big number going towards 0. 5 over a really big number. Even though you square root it, it's still really big, right? And so that is 0. 11 as t goes to infinity. Negative 1/2. Because high powers dominate. 3 and the 5 don't really matter. You got $1 billion times 2. You add on 3. The 3 doesn't really matter. 2 matters. I mean, you have $1 billion. That got $2 billion. I mean, that matters. But you add on $3 to $2 billion. Doesn't really matter. So this is basically 2t over negative. Don't forget the negative. Negative 4t. 5 doesn't matter. High powers dominate. Cancel. Cancel. Negative 1/2. Okay? When x is getting really large, high powers dominate. Okay? All right. But then, see now, so you got to be careful. This is one of the problems we're going to have on the quiz, is that you get this in your head, but then now this one looks exactly the same, but it's t approaches 0, right? So we substitute. And even here you can substitute. Even here you can think substitute. Even though it finishes that number, you can say, well, 2 times infinity plus 3. Hopefully at that point you go, oh yeah, but the plus 3 won't matter, and you start thinking that way. Okay, so what do you get on this one? 3/5, right? 3/5. Just plug in a 0. Okay, you always start with direct substitution. Okay, x gets really big. High powers dominate, so that doesn't really matter. You got x squared over x, which is just x, but that's not your answer. The answer is, yeah, so what do we put? So yeah, let's make sure we talk about it. This would be an okay answer right here. This would be the example that I was showing right here. Okay? This is remember, if it's not a number answer, you better have DNE on there. Limit does not exist, and it's going to infinity. Now, the back of the book might have just said infinity. If you type this in your calculator, it probably just says infinity. Okay, but those are kind of shortcuts, and those that we're going to say does not exist. That is the actual answer. Now, but it does go to infinity. We don't have to check left and right because you can't do the left and right as x approaches infinity, right? So this is just getting big, positive, okay, as x goes to positive infinity. All right. Now, if this said negative infinity, x went to negative infinity, this would be negative infinity, right? Because the answer is just that. Okay? All right. What about this one? 1/2, right? Those don't matter. High powers dominate. X squared over 2x squared. X squareds cancel. Make sure you put 1 up there so you don't say 2 for your answer. It'd be 1/2. Okay? What about this one? I think we had one similar to this the other day. That's going to 0. Because what you have is the top is just, again, plug in. What is sine of infinity? Well, I don't know if you can plug in. But you just got to think. As x goes way out to the right, that's what x approaches infinity means. As x goes way out to the right, the sine graph just bounces back and forth, but the bottom's going to get bigger and bigger. Okay, so the bottom gets bigger and bigger, the fraction gets smaller and smaller. That's going to bounce back and forth between positive and negative, but it doesn't matter. It's heading towards 0. Okay, what about this one? The top is going to be negative infinity. I'm just thinking about plugging in here first. So the top's going to be really big, but cubed, it's going to be negative, because when you cube a negative, it's still negative. So the top's going to be really big. And then cosine just bounces back and forth from -1 to 1, right? When you add that onto 2, that's going to bounce back and forth between what, 1 and 3? The bottom's just going to bounce back and forth between 1 and 3. Okay, as you go way out to the left on cosine. Okay, or you can think of the cosine graph shifted up 2, right? Think of the cosine graph shifted up 2. It's just going to bounce back and forth between 1 and 3. So you're going to take a really big negative number and divide it by 1, 2, 3, something like that. What's it do? What's that going to do? Just going to be negative infinity. Does not exist. Negative. You're just getting a negative trillion, and then you're going to divide it by like 2 or 3, 2.7 or 1.8 or whatever. Right? It's just going to keep getting really big and negative. Okay? So that's it. I mean, that's how you think these through. That's it. I mean, so on some of these, it really is with infinity. It's really about just thinking through what's happening. Okay, here's what I was talking about. Now, this is a fact. This is actually in the syllabus for AP Calculus. To just understand about basic functions, what they're like, okay? The exponential functions, any exponential function like this will eventually outgrow any power function, that looks like an x cubed or an x squared. Any exponential function, assuming base greater than 1, right, that goes like this, not exponential decay, obviously, will always grow faster, eventually, than a power function. Now, I think about another time when this is useful. There was a question I remember once on our midterm review, or maybe it was on the AP test, where they had to basically, they were given a couple of graphs. They were asked somehow how many times they crossed. Somehow they had to figure out how many times they crossed, or they were equal. And it was an exponential in the power. And when they graphed it on your calculator, it was like kind of a parabola. It kind of went like this. And then the exponential kind of came through here like so, and it crossed, and it crossed. crossed and it looked like this. And so when you graphed it on your calculator, it looked like that. So how many intersection points were there? That was kind of the question. And it was multiple choice, 1, 2, 3, 4, right? Well, what's the answer? 3, right? It's 3. Because this isn't, it's poorly drawn, but this is an exponential. So eventually it's going to grow, fast, go really, really steep. And this is just going to kind of keep going like this. Eventually they're going to cross again. They are going to cross again. Now you would never on your calculator probably ever set the window big enough to see that. And if you just look at it on your screen in kind of a standard window, this looks like it's really pretty flat and not really growing very fast. But eventually, any exponential is going to grow and go steeper and grow faster. And so eventually these are going to cross again. And there would be 3 intersection points. So having that knowledge about these kind of functions is what they were quizzing you on.
Also just like solving so they equal each other.
Yeah, there was for some reason, it didn't work, or maybe it was a no calculator, and so the easy thing to do was to plug. I don't remember. There was, for some reason, and I didn't, right now it escapes me. You're right. Yeah, you can just, where do they cross? You just set them equal to each other, and maybe the calculator. Sometimes you get the thing that says warning, more solutions may exist. I wouldn't think it would get fooled on that one. But anyway, that was just one that kind of comes to mind. So that's just a basic knowledge of these exponential functions we need to have. Okay? And so that's what helps you here. So as x goes to infinity, so what we have is infinity over infinity. We have a big number over another big number. They're both getting really big. But just understand this one is getting way bigger than that. Okay? So the answer? What's the answer? Does not exist. Infinity. Okay? Because the top is getting bigger way, way faster than the bottom. They're both positive. Okay? So it's going to be positive infinity. All right? Well, then they give you the very same thing, except they say x goes to negative infinity. Well, the bottom's still getting big. Right? Negative squared is going to be positive. It's going to get really big. What about this?
Really small.
That's getting really small. Because you're going to have 2 to the negative 100. Well, that's 1 over 2 to the 100, right? That's very, very small. That's like a 1 over infinity, which goes towards 0. Well, now, so what's this going to do? That's 0. I mean, that's going to 0 in a hurry. Because the bottom's getting really big, which makes a fraction go to 0. And the top's getting really small, which also makes a fraction go to 0. And so the two together really will make this one go to 0 in a hurry. Okay? So. All right, now, so 19, and that was one you guys asked about. This one takes what we just talked about and flips it. Okay? So, if any exponential is going to get way, way steeper than any power function, right, like a parabola, then what about their inverses? Because that's really what ln x is. ln x is this. Well, if b to the x, if an exponential is going to get really, really steep, almost vertical, then what do you know about ln x as it goes out here? Almost horizontal. It's pretty much just flat. Not quite, but pretty much. Okay? So it's getting big, but not very fast at all. Now, what's the invert? Now, I said x to the n, so I guess there I mean x squared, x cubed, something like that. The inverse of x cubed is x to the 1/3. So this is actually what x to the 2/3, because of the 2 on top, it won't go negative. Here's what x to the 1/3 would look like. It would be the inverse of x cubed. That's the inverse of x cubed, right? Because we all know it, hopefully we all know that x cubed comes up and does that, right? X to the 1/3 would do this. It's very flat. Okay? X to the 2/3, the 2 just would be like squaring it, so all the negative would turn positive and then change a little bit because it would be squared. But basically x to the 2/3 comes in and does this. Which one of these is flatter, do you suppose? LA. ln is flatter because it's the inverse of this. So exponentials grow really, really steep, so ln is going to be really, really flat. This is going to be pretty flat, but it's not going to be as flat as ln. So this is, they're both getting big, right? They're both getting big, but which one's getting bigger? Which one's getting bigger faster? The bottom one, right? The bottom one, because this is so flat that it's getting big, but pretty slow. Okay, so this is getting big, but that one's really getting big. So this is going to what? 0. Okay, so that could show up on the quiz as well. Okay, just know this relationship here of comparing a power to an exponential, and then their inverses, which would be a fractional power like 1/3 or 1/4 or something like that, and an ln or any log. Okay, logs are real flat because exponentials are really steep. Okay, so understand that relationship. That could play a role in these as well. Okay, all right, 20. So now again, we're just plugging in. So infinity, well, what happens if you get pi over something really big? That's just 0. It's going towards 0. So what's the sign of 0? So direct substitution in a sense. So there's one where you actually do the limit of kind of the inside piece, and then whatever that is, then you can just do sine of 0, and that is 0. Okay? And what about this one? You're just going to plug in a 0. Sine of 0, 0. Sine of 0, 0. Almost too easy. Seems like at the end it should have been harder. Okay? And all of a sudden that one just direct substitution. Okay? All right. Before we do this next thing here, let's let's talk about this one right here. Matter of fact, everybody just do this one right here, because this didn't come up in any of ours today. So just do that one real quick. See what you remember about this. This is just a quick review. Okay, so in our last quiz, you did on this. Right? You plugged in a 3. You got 14 over 0. You just said that does not exist, and then you stop, right? Now, on Wednesday, you're going to do what? You're going to check left and the right of 3, right? We didn't run into any of those, because what we have here is a vertical asymptote, right? What we have here is a vertical asymptote, so this would be an example of this scenario we were talking about here, right? One of these kind of situations, right? So you're going to check the left and the right. And so we get left of 3 is 2.999, right of 3 is this. 14 I don't care about. I mean, this would be left of 3 would be a little less than 14. This would be a little more than 14. Who cares? But what does matter is 2.999 minus 3 is going to be a very small negative, which means that's going to divide into negative infinity. It's going to divide into positive infinity. So all of that would be good to see Well, for sure, I need to see that and that and that and that, and this part, I suppose, could you be doing in your head? I suppose, so if you didn't write that down, it wouldn't be probably the end of the world. But again, as we think about our midterm when we come back, and late January, early February, showing work, communicating, explaining your reasons, that kind of thing, it's just a good habit to get into, to be doing that stuff. All right, so before we go into this next thing here, talk a little bit about infinity again, and this strange thing that infinity is and how it's hard to grasp. And I had a professor in college told us this story, and I've always remembered it. And so it's a story of the Infinity Hotel. And the Infinity Hotel has an infinite number of rooms. Okay? And it's full. Somebody comes, every room's numbered, 1, 2, 3. Every room has a number. Right? There's an infinite number of them. And every room's got somebody in it. Okay? And somebody comes and wants a room. And the manager says, what? You're full? No. He says, no problem. We're full, but no problem. So what's he do? What's he do? How's he get him a room? He says, everybody, he gets on the intercom. This is one of the downsides of staying at the Infinity Hotel, because this can happen to you almost always. But it's probably not full all the time. Everybody need to pack up your stuff, and you need to move to a room with a number 1 bigger than the room you're in. Possible? Possible, right? Everybody's in a room with a number on it. Everybody just moved to a room that's 1 bigger. Right? I mean, he couldn't, so you say, well, geez, that's inconvenient. Why would you ever want to stay there? Why would you do that? Why didn't he just send them down to the inn? There is no inn. There is no inn, right? There's no open rooms. He can't send them to a room because there's no open rooms. But he can tell everybody to look at the room number you're in and pick up your stuff and move to a room that's 1 bigger, because it'll be empty because those people have moved, right? And then what's open? Room 1 is open. That's straight. Okay? So then, a big group comes and they need 10 rooms. He says, well, we're full, but I can get you in. What's he do? Gets on the intercom and says, hey, everybody, need you to pack up your stuff and move to a room that is 10 higher than the room you're in. Right? So everybody does it. And a little farther to walk, but they get to their room. Now there's 1 through 10 is open. Right? Number 1 went to 11, 2 went to 1 through 10 is open. There you go. Wow. Good deal. Okay, well, then a really big group comes. And this group needs an infinite number of rooms. He says, well, we're full, but we can do it. What's he say on the intercom? What's he telling you? Now, if you've heard this before, go say. Can he do what he's been doing before? That doesn't work. You can't get up and say, hey, take whatever room number you're in and move down an infinite number of rooms. What's he do? He gets on the intercom and he says, okay, everybody needs to look at their room number, multiply it by 2, and then move to that room number. So what happened? So everybody's in what room? Everybody's in an even number of rooms. So if you're in the room 1 million, you have to move to the room 2 million. Now, so there could be, so they've got some elevators and escalators and maybe even a transporter. I don't know, they could be whatever. But everybody's now in an even room. How many even rooms are there? Infinite. So they can all fit. And so now all the odd rooms. So then they have big. I like that story just because it just, really, the place is, I mean, in a sense, the place is full, and all of a sudden it's half full. Half full. Right? But that's what infinity, and that's what's weird about infinity. Okay? Trying to fathom, the different sizes of infinity. Okay? So, all right. Let's take a look at this thing called L'Hopital's rule. So do those two right there real quick. Now we said you always start with direct substitution, right? So on number 1, you start with direct substitution. What do you get? 0 or 0. Of course, 0 or 0 always meant keep going, right? And we had some algebra we could do. In this case, it's our easy kind of algebra, I suppose, which is our factoring. And then you can plug your 2 back in, and you get what? 4. There's your answer. Now, we also had conjugate method. We also had the bow tie method. Now, you notice we haven't practiced that. And it's kind of like, maybe we should practice that. It's what we need. Well, that's the reason we haven't practiced it, because we're going to learn this thing called L'Hopital's rule, which we could actually use in those cases, which might be an easier thing to use. But you can still use those algebra techniques, okay, like we just did here. Okay, what about this one? What's the answer now? 3/4? 3/4. Again, high powers dominate. Now, essentially, this is infinity over infinity, isn't it? I mean, if we're going to do a direct substitution, kind of, with infinity, this is getting really big, this is getting really big, right? Top, bottom, both getting really big, infinity over infinity, right? But that's not 1, just like 0 over 0 is not 1. It means keep going, okay? But in this case, what it is this, these don't matter. High powers dominate. This is essentially 3x squared over 4x squared. The x squareds cancel. This is 3/4. There you go. Okay, 2 potential quiz questions just like that right there. Okay, now we're going to look at an alternate way to do those. And this is called L'Hopital's rule. Okay, L'Hopital's rule, let's see, is listed in your book on page 229. L'Hopital's rule, now I'm going to write it a little different than what they have. But basically, L'Hopital's rule says this. If the limit as x approaches a of f of x equals 0 over 0, or the limit as x approaches infinity. Now this could be negative infinity too, so it doesn't matter. Of f of x over gx equals infinity over infinity. Basically, it's saying that the two examples we just saw, basically they're saying if you get 0 over 0 or infinity over infinity, then you can do L'Hopital's rule. Okay? So if you get 0, so the only way you get 0 over 0 is if you plug in a 2 or a 3 or something like that, right? You're not going to get infinity over infinity if you plug in a 2 or a 3, right? And if you do x approaches infinity, you're not going to get 0 over 0, right? You're going to get infinity over infinity, something like that, okay? I suppose maybe you could get 0 over 0 here, whatever. All that first part is saying is before you can use L'Hopital's rule, you have to have either 0 over 0 or infinity over infinity. That's what it says. Okay? Then the limit of f of x over g of x, and I'm not even going to put in the x. It could be x approaches a, or it could be x. I guess I'll put it. It could be x approaches a or x approaches infinity. It doesn't matter. Is equal to the limit x approaches a or x approaches infinity of f prime of x over g prime of x. Now remember, chapter 4 is all about using the derivative, right? Now that we've done the gateway test, now that we've learned how to do the derivative of all kinds of functions, what good is that? What uses are there of the derivative? Now we've already talked about, obviously, the chart, maxes and mins, and we've kind of delved into it a little bit about where we can use the derivative. Chapter 4 is about all kinds of applications. Where can we use the derivative? Here's a mathematical use of the derivative. And what it's saying is, if you've got a limit where the top and bottom are both getting small, or you've got a limit where the top and bottom are both getting big, the limit depends on how fast they're getting small, or how fast they're getting big. I told you this last week, right? And what measures rate? What measures rate? The derivative, right? The derivative. That's what it is. Instantaneous rate of change. Okay? So therefore, we can use the derivative of the top and the derivative of the bottom to find how fast they're changing and divide those, and that will give us our answer. In many cases. Sometimes it may not. It still might be does not exist. Okay? But we can do this. Now, the danger is, especially if you haven't passed the gateway yet, when we're doing L'Hopital's rule, you're doing exactly what you can't do when you're just doing a derivative, which is just do the derivative of the top and derivative of the bottom, right? We can't do that. We got this thing called the quotient rule. So we're not doing the derivative of that fraction. What we're saying is to find the limit, we can do the derivative of the top function, the derivative of the bottom function to get the limit. So you just can't confuse those two. Okay, you can't confuse those two. We're doing it this way for a specific reason. Okay? All right. So back to these two that we just did. So once we got to here, we could have said, aha, we could use L'Hopital. So what's L'Hopital say? Do the derivative of the top. What's the derivative of the top? 1. What's the derivative of the bottom? 2. X. Plug in a 2. 1/4. That was nice. Alright? That was nice. So we didn't need to factor and cancel, or bow tie, or conjugate method, right? To get that. Alright, let's look at this one. Infinity over infinity. Aha! L'Hopital. What's the derivative of the top? 6x. What's the derivative of the bottom? Minus 1. Plug in infinity. Oh, still infinity over infinity. What do you suppose? Do it again, because you still have a limit where you're getting infinity over infinity, so you do it again. Derivative of the top? 3/4. L'Hopital's rule. Only works, and I cannot emphasize this enough, only works when you have 0 over 0 or infinity over infinity. Only works in those cases. So, we go back to this, we go back to our homework. Right? I give you this problem on the quiz. L'Hopital's rule? No. It's 3 over a really big number, it's 0. So it isn't an answer to everything. Right? L'Hopital's rule? No. Just think it through. Okay? L'Hopital's rule? Here it would be. It's infinity over infinity. Now it's infinity over negative infinity. It doesn't matter. Right? It's this getting big, this getting big. Derivative that's 2, derivative that's -4. -2, but that's just as easy. To be honest, why use L'Hopital's rule there? That's just easy. High powers dominate, -1/2. Right? I mean, even on this one, even on the one we just did a minute ago. Right? This one, it's just about as easy to say high powers dominate, 3x. I mean, that's almost as easy. So L'Hopital's rule wasn't that much better there. Okay? But if you get into ones with e's and other stuff in it, it might be not bad. Okay, let's keep going here. So, L'Hopital's rule? No, remember that one? We put in a 0 and just got 3/5. 3/5. That was it. We're done. Okay, L'Hopital's rule? X approaches infinity, what's the top? Infinity, what's the bottom? Infinity over infinity. L'Hopital's rule? Sure. What's the derivative of the top? 2x. What's the derivative of the bottom? 1. As x approaches infinity, what's that doing? Going to infinity, right? As x goes to infinity, this is going to infinity. So it does not exist, infinity. But we could have thought of it as L'Hopital's rule. But we could also have thought of it as high powers dominate. They're about equal. I don't know the one's better than the other. Okay? L'Hopital's rule, infinity over infinity, that would work. So, derivative of the top's 2x, derivative of the bottom's 4x. Infinity over, or just cancel an x at that point, 2/4, 1/2. Not bad. Okay? What about this one? L'Hopital's rule? No. It's -1 to 1 over infinity. That's not L'Hopital's rule. This is a classic one where people would look at this and they'd want to do L'Hopital's rule. Right? And if you do that, it doesn't work. You get cosine x over 1. X goes to infinity. Cosine infinity, that's -1 to 1 over 1. No, it doesn't work. It doesn't work. It's not infinity over 0 over 0. Okay, 16. This is infinity, negative, but this is bouncing back and forth from 1 to 3. So this is not L'Hopital's rule. Can't do it. Okay, this was infinity over infinity. Right? But we said this one was way bigger than this. Well, let's do it. What's the derivative of the top? Times ln2 is just a number, and this is 2x. So this is still infinity over infinity. Right? Do L'Hopital's rule again. ln2 is just going to hang out there. 2 to the x would be 2 to the x ln2, and then you got that ln2 that was just hanging out. And what's the bottom? Derivative of 2x is 2, right? So now what? As x gets really big, this is getting really big. These numbers don't really matter, but it's getting really big. It's getting really big over, divide by 2. That's getting really big. So it does not exist infinity. But that would have been a little easier, especially, I mean, now that you know that exponentials grow so much faster than that, you could probably just think of it that way. But L'Hopital's rule would work there. You'd have to do it a couple times. So you may get into product rules and all kinds of stuff with L'Hopital's rule, depending on what's on top. Okay? All right? Now here, we would not use L'Hopital's rule, because this was getting really small, this was getting really big. So this was not a 0 over 0 or infinity over infinity situation. Okay? This was infinity over infinity. Well, what's ln x? Derivative, 1 over x. What's this derivative? 2/3 x to the -1/3. Now, what do you suppose you do with that? Sometimes this happens on L'Hopital's rule. You do L'Hopital's rule, and then you look at it, it's quite a mess. Well, do some algebra. What can we do with this mess here? And flip that up there. So this is x to the -1, so I would make this x to the -1. I would flip this up there, that's x to the 1/3. This 2/3 would flip up, be a 3/2. Couldn't we do that with all that right there? Now we can add those powers. What's -1 plus 2/3? 3/2 x to the -2/3. Now we can flip that to the bottom. 3/2 And then this would be x to the 2/3. I couldn't put the 2 down there, whatever. Now, look at that. As x gets really big, what do you got? Bottom getting big, top just staying 3/2. So bottom gets big, this goes to 0. So again, and a lot of you ask about 19, right? Now maybe now with LN, now you kind of got the idea of which one grows faster, that kind of stuff. But here, L'Hopital's rule, if you're somebody who likes a formula to plug into and something to do, L'Hopital's rule is great, right? Because this is getting big, not very fast. This is getting big, not very fast, but you're both getting big. It's infinity over infinity. So we do L'Hopital's rule. It looks a little messy. Maybe do a little algebra to simplify it. Now look at it as x goes to infinity. Oh, clearly it's going towards 0 now. Okay, so it shows it more clearly. All right, this one was not a L'Hopital's rule. This was not a L'Hopital's rule. Okay, now sometimes you can do L'Hopital's rule just on the inside piece, right? Like let's say this thing on the inside was a 0 over 0, right? So you can do L'Hopital's rule just on that inside piece, get what that was. Maybe it comes out to be 3, and then you get sine of 3 would be your answer. Right? Because there'd be no calculator, so you just leave it like that, sine of 3. I mean, let's make one up. Sine of, let's do, like we just had a minute ago. Let's say we had that as x approaches 2. Right? Let's say we had that as x approaches 2. So now you plug in your 2, you get 0 of 0. Right? So just do L'Hopital's rule on that part. So that was 1 over 2x. Okay, now plug in your 2. What do you get? 1/4. So now you get 1/4 in there. So now the answer is just sine of 1/4. And that's your answer, right? So sometimes you do L'Hopital's rule in a piece of it, where you get 0 over 0 or infinity over infinity. Okay? All right. So, indeterminate forms. So, 0 over 0 clearly is an indeterminate form. Infinity over infinity is an indeterminate form. And then there's one more that we talked about. This one. Now, you can't use L'Hopital's rule on that. But anytime you have 0 over, or anytime you have 0 times infinity, you can turn it into one of those. Think about it. And it goes back to something we talked about towards the beginning of the period. Remember how we said 1 over infinity is basically the same as 0? Right? I mean, think about it. Basically what we're saying, there's a reciprocal of big is small. Right? Reciprocal of big is small. And likewise, reciprocal of small is big. Right? Well, think about what you can do. Anytime you have 0, you can flip it and turn it into that. Well, what do you got? Infinity over infinity. Right? You got infinity over infinity. Now you can do L'Hopital's rule. Or you can flip, you can change your infinity to 1 over 0. So what do you got? You got 0 over 0. Make sense? So when you have a 0 times infinity, you can turn it into a 0 over 0 or infinity over infinity kind of situation. Let's look at an example right here. Okay, so you got x times e to the negative x. Now, as x gets really big, this is getting really big, and this is getting really small. Right? 0 times infinity. But what can I do with that e to the negative x? Flip it to the bottom. Now what do I got? I got infinity over infinity. Now, we know, we just talked about this. Which one of those is getting big faster? E to the x. So what's the answer to this going to be? 0. We don't need L'Hopital's rule. It's just there if you want to use it, right? Sometimes it's going to be really nice. It's going to be by far the best thing to do. And other times, maybe, but I don't even think you need it here. Right? But you can do it. Once you write it like this, L'Hopital's rule basically always has to be a fraction. Because it's got to be 0 over 0 or infinity over infinity. It's got to be. So now we can do the derivative. Top is that, bottom's that. Now what happens is x gets really big. Now we got 1 over infinity. Oh, okay, that's it. So we can do L'Hopital's rule once we get it rewritten like this. Okay? All right. What if you had, trying to think of something that's not so obvious. That one just flips like that. Okay, yeah, actually, here's one right here. Here's one right here. Okay, I thought that. All right, right here. As x approaches 0 from the right. Now, why aren't we approaching 0 from the left? ln, you can't put in a negative, right? So there's not a car on both sides. So if you see one of these, it probably means there's a reason why I'm doing that. So, okay, the only time we're going to have to worry about left and right is when it does not exist, and we got to check the cars on both sides, okay? So what do you got here? Well, this is going towards 0, and as x approaches 0 from the right, what's ln x doing? What's ln x doing as a car comes from the right of 0? Negative, it's going down there, right? Going to negative infinity. So we have a 0 times infinity. So somehow we got to flip one of these. Okay? Now I think I would flip this one. So what would that be? I would leave the ln x, ln x on top, and then how would you write this down here? X to the negative 2. We don't do that very often. It's not like we flip a positive down, but it would be. It would be that, right? Now what we have is an infinity over an infinity situation, right? Because what we have here is 1 over x squared. 1 over something really small is getting really big, right? So now we've changed it to an infinity over infinity. Now we can do L'Hopital's rule. So now we can do the derivative tops, 1 over x. Derivative bottoms, negative 2x to the negative 3. And now we can do what I was talking about a minute ago. Make this x to the negative 1. Let's flip this up. That's x cubed. We still have the negative 2 down there. What do you get on top? X squared over negative 2. Now as x approaches 0, what do you got? X approaches 0, plug in a 0. You guys aren't very confident. 0 divided by negative 2 is 0, right? 0 divided by negative 2 is 0. So 0 times infinity, the zeros win, right? Remember, we talked about this really slow. Really slow. ln x is going towards infinity, but really, really slow, right? Kind of thing. All right. So, what do we got? This one worked right here. Okay. Oh, yeah, no, I did that right. Yes.
On the previous example though, wouldn't it be like the bottom, wouldn't that be like 0 to x to negative 7? So that would be small, because it's the negative.
Oh, right. But it's x approaches 0. So it's 1 over x squared. So it's 1 over really small. It's really big.
Oh.
All right. So on your homework sheet here, it says 4.2, day 2. The M4 means multiples of 4. Okay. As far as the particle motion, I think what I would do is probably go back to this first packet we did on particle motion and make sure you're good on all those things, and don't have any questions on that all the way up through page 16. Okay, because there's some ideas up there that with tables and graphs and stuff that I may take off the quiz, and so I'll ask if you have any questions there. So go back and revisit that packet on 1 through 16. Make sure you're solid on all that. Okay, and then the 4.2 in the book, day 2 off of your sheet here.